In this video, we'll move into section 7.4 and discuss the technique called partial fractions. There's also a quick little extra U-sub information that we'll cover at the end. And basically, this is our last higher level integration technique. So, just before I jump in and start talking about this new technique, just one quick thing to point out. Even after we finish this section and we get through section 7.5 and we discuss general strategy, and we'll quickly mention a few items from 7.6 using computer software or integration charts to solve some other integrals. But even with all those tools, we still have to recognize that integrals and antiderivatives are still more complicated than derivatives. After everything we've done, I don't have to work hard to make an integral that you can't solve. Something like that. So again, that's why we are still building a lot of information, we're developing a lot of strategy, but even after we finish all of this, it's still not enough. So that's going to motivate us as we move past this section. That's not the only reason, but that will be one of them. No matter what we do after this, it's not just a trig integral because it has the x squared here and there's no other trig functions. You might think a u-sub would work, but that doesn't get you anywhere. No clever fancy u-subs will work. Again, that one is just going to be completely stuck. And that's not that complicated as far as looking at the integral and looking at its pieces and components. That one does not look very complicated. So again, that's not something we're going to get to for now. That's not something we're going to get to until pretty close to the end of the semester. But back to this idea of partial fractions. This is not even really an integration technique. It's actually more of just an algebraic technique, but when we apply it to the right circumstances, it leads to a better integral. So what we are going to do here is be a little backwards to what we're accustomed to. If we were just looking at numbers and we had the fraction 7/12, well, there's no motivation to do anything with it, but especially if I write this out, we can realize that 7/12, it's still a regular fraction. It's not compound. The numerator is lower than the denominator, so it is a proper fraction. But I could break it into these smaller, more basic fractions. That's the idea we're going to. So one very, very quick one to try and give us some motivation. If we expand that and not just look at numbers, if we actually look at algebraic expressions, we can take the fraction minus 7 over x squared minus x minus 12, and that could be broken down into 1 over x plus 3 minus 1 over x minus 4. Now again, that's a little backwards to what we're used to. It's a lot more common for us to start with two separate fractions separated by addition or subtraction, get a common denominator, and combine and make them into one fraction. So why would we be interested in going backwards like this? Well, think about this as an integral. Instead of just fractions, if I was trying to solve this exact integral, well, nothing good really happens here. All of this is going to be based on algebraic expressions. We're not going to be looking at trig, and at the end we'll talk about some radicals, but at the beginning, these are all what we call rational functions, where we have a polynomial over a polynomial. And one of the keys will be that this has to be a proper rational function where the degree of the numerator is smaller than the degree of the denominator, similar to regular fractions where just the numerator has to be smaller than the denominator. That's what makes this a proper fraction, and that's kind of the same idea here, that this is a proper fraction. But if you thought about integrating this, well, there's nothing really good to do here. You may try u as the denominator, and that's not going to work. Even if you remember some of those fancy u-subs that we've talked about, any other manipulations like with completing the square, there's still nothing good is going to happen here. But if I realize how this denominator could be factored, and that's where these x plus 3 and x minus 4 are coming in, if I realize how this could be factored and I could break it into its smaller components, well, initially this seems like we'd be making our lives more difficult because we started with one proper fraction and now we've broken it into two. But both of these are much more basic that with just a little bit of work, some of you may need u subs here, but both of these, now they're two separate fractions separated by subtraction, so that's why I'm allowed to think of them as two separate integrals and integrate each one separately. And when I do that, again, maybe you want a u sub here, there's a little bit of division, but both these are pretty basic. If you pick u as the denominator, du equals dx, both of these become 1 over u, so both of these have antiderivatives log of u. And especially if you're a little, rusty, and if you haven't got so much practice, again, you should certainly be able to integrate both of these, verify that these are the same, that these are the answers, or take the derivative and verify, yes, the derivative of this 1 over x plus 3 times a 1. That matches. Minus the derivative of this 1 over x minus 4 times 1 matches. So again, we could certainly confirm this and realize this is the correct answer. The very, very last thing here, I would never have a problem with this as an answer, but just to realize this is where, again, the book likes those little properties of logs and would not be surprised at all to see the book write this answer in this way, by looking at the subtraction between these two logs, so to bring those together as one log with those two being connected by division. The division inside the log, the same as the subtraction separating the two logs. Okay, so that's the direction we're going. We'll redo this problem to see where this came from, but that's the motivation of partial fractions. Start off with a proper fraction, but a fraction that you're basically stuck with, break it into smaller fractions so that we can integrate each of these smaller, more basic fractions. We're going to see a lot of logs come up here. That's not the only thing we'll see, but again, that'll be a very common situation that comes up. The other thing before we get too deep into this is the reminder that for a fraction like this, you've got that x squared plus a squared form, so some of us might jump to trig substitutions, but that's a little bit harder than it needs to be. That we've seen examples like this before, that individually each of these pieces can work nicely with the denominator. So if you separate this into two fractions, it's not quite the same thing I was showing you here, but we've seen this. By separating this into two separate fractions, not playing with the denominator, just breaking the numerator up into two separate pieces, now this can be done very nicely. Once again, we treat them like two separate integrals, now separated by addition. Here you'd have u as the denominator, that's what would work, and you'd end up getting 1/2 times 1 over u, so 1/2 times log of u, and then this one, well, that's just inverse tangent. So again, I did that one quickly as well, but we've also seen that one before. So that's just another quick reminder. And again, if you forgot that, it's definitely a good reminder. You did need a u sub here, but don't use that u sub here. Again, you're treating them as two separate integrals. This one, they both have some problems, but that one is a direct antiderivative that we know. That's the inverse tan x. This one, not quite so simple, but again, u as the denominator will give you an extra 1/2, 1 over u, and that's how I got the log of u. Also, a very quick reminder, a couple of you missed this on the Chapter 6 test. Remember, when you get antiderivatives that give you these natural logs, you need the absolute value. There might be a few occasions where, like, if this was a 2, that becomes a squared. Well, squaring this will make it positive so that you could drop the absolute value, but that's more of a rare, lucky situation. The good habit is make sure you keep the absolute value on those answers. Okay, that's the direction we are going, everybody. Starting with these complicated fractions, but still proper, to then move into this form. The book gives you a quick reminder, again, about proper fractions. If you don't have a proper fraction, for instance, if you had x squared over x squared plus 1, now you have the same degree top and bottom. You need to divide this before you consider any of these other strategies. So example 1 kind of goes over that a little bit. The book kind of expects you to remember polynomial division. I'm not really going to bust your chops too much on that, but especially when the degree is the same, here's a nice little trick, a nice little technique that can help you here. Again, you could set a polynomial division. How many times does x squared go into x squared? 1. Multiply everything here, but now you subtract. These cancel, but I'd be left with -1. That's your remainder, and the remainder goes over the original divisor. So again, polynomial division, anytime the degree of the top is equal or bigger than that of the bottom, you can apply ideas like this, and then this is what you'd be left with. And once again, now it's 2 pieces. It's not always going to be 2. There might be 3 or 4 pieces, but pieces that are now separated by addition, subtraction. Both of these are nice and basic. The anti of 1 with respect to x is x, minus the anti of this is inverse tan. So again, doing that actual division may be the key to getting an integral that we can now handle. But the trick I was mentioning, a slight little alternative here, it's still going to take us to here. All these new techniques, I really hope you've realized that whether it's integration by parts or the trig substitutions, or same thing here with partial fractions, none of these techniques actually solve the integral for you. They're all about manipulating that integral in some way to make it something, to get us to a point that something else would work. Whether it's just a known antiderivative or a u sub, but that's the idea of all these new techniques. So this little trick is just about making everything perfect. It's kind of doing this, but just making it so everything matches perfectly. What I would do is I would add in an extra +1 -1 in the numerator. The reason I'm doing that, again, this is a manipulation. I can't just change it. I can't just add a 1 or subtract a 5. Whatever I add or subtract, I have to keep it balanced. So just combining like terms here, yeah, the 1s would cancel and you go right back to where you started. But the idea of doing this is, again, clever breaking up of the fractions. But now I'm not just going to take the x squared over this. I'm going to take the x squared and the +1 over the original denominator, and then this is where I'll cut it off, minus that last piece over that same original denominator. Again, it's getting us to the same place we were here. The reason I chose a +1 -1 was that this would match perfectly. So now these completely match and cancel. There's your 1. And then what was the remainder here was just kind of the leftover place here. But either way, started with this, went here to here, then got to here, and then we could finish with the antiderivative, or did our division to get to here to then get to a spot where we have a good, you know, again, good friendly integrals, stuff we know how to handle. So all this is a good warm-up. Now let's really get into the idea of how we get into those partial fractions. How do we get from this ugly fraction to these more basic fractions? And we refer to this as the partial fraction decomposition. That's what we formally call this. The way to do this is, again, you know, our book doesn't exactly give us a step process. It kind of gives us some idea and then jumps in. So I'm going to be a little informal here, but similar to what the book suggests, we're going to need some practice applying this. So, just looking at the partial fraction decomposition, and to just take a moment and realize, just like we said with the trig subs, it's possible that we may just ask, what is the decomposition? Just set it up, do not solve the integral. And that's just working on getting from here to here, but not even knowing what these numerical values are. Because the idea of the partial fraction decomposition, well, step one is, as we keep saying, we need a proper rational function. And by that, we're talking about a polynomial over a polynomial where the degree of the top is smaller than the degree of the bottom. Everything we've been talking about before we got to this point. Now from here, we will completely factor the denominator. And then after that, each power for every factor gets its own proper fraction. Now, after that, at this point, we'll know what the denominators of the fractions look like, but we're going to have generic variables for the numerators. After that, if we're going to completely solve, this is all you would have to do to just do the decomposition. But if we're going to take things further, we're going to need to know what those values are, and then we could finish and solve the integral. So let's start off, and again, I'm still going to keep picking on this initial problem, and then we'll keep adding more and add more examples. So if we started off with minus 7 over x squared minus x minus 12. For this next section, all the directions are just going to be set up the partial fraction decomposition. And I'll even put an extra note. Do not solve for A, B, etc. Because what we have, we see this is already a proper fraction. We go to the denominator, we factor it completely. So this one's a nice, quick, simple x plus 3 times x minus 4. Just nice trinomial into two binomials. So I'm going to end up, both of these are to the first power, so I get a fraction for every power of every factor. Well, there's only two factors and they're both to the first power. So I'm going to get a fraction for each. Now, I know I ended up with this being a minus at the end, but for good habits, we'll always write it as a plus. And then the value here, if this ends up being a negative, then we could kick that sign out in front. But do yourself a favor. It's always easier to connect these fractions with addition in the first place. And if we do get any subtraction, that'll come up as a result of our solving. But again, we're still not done because we know what the denominator should be, but we don't know what the numerator should be. But if it is a proper fraction on this side, then both of these will also be proper fractions. So if these denominators are both degree 1, the numerators have to be degree 0, meaning there can't be a variable. There can't be anything more than a number up here. We just don't know what that number is, and that's why we're going to use letters like this. So I don't know what number goes on top of this fraction, so I'll just assign it an A. And then I don't know what number goes on top of this fraction. There's no good reason for me to think that these could be the same number. They might, we might get lucky, but there's no good reason for me to think that. So I'll use a different letter. That is the decomposition for this very first problem. But now let's keep going here. Number 2. So this is number 1. There was the problem, there's the answer, and that's it. Getting your basics. Before we get so deep into solving the integrals, first things first, make sure you understand this decomposition. That's the first step. Solving for these letters, that'll be the second step, and then we'll just keep escalating. But number 2. Number 2, I'm going to do you a favor. I'm going to, it doesn't matter what the numerator is here, 12x minus 5. And in the denominator, I'm going to already factor it for you. Let's say we've got x times x minus 4 times x plus 1 squared. I'm just going to set up the decomposition. Don't try and solve. I can't say that enough. When we get to the solving for these letters, you'll notice that we're really only going to be able to handle, I don't want to say just basic ones, but ones that are at least a little bit more not too involved. You'll see there's a lot of equations that are going to come up here in a few minutes. So basically, we can't solve if there's more than 3 letters without some other extra computer software or some extra letters on solving those types of equations. So this, again, I'm saying all that so that you realize this is just purpose in breaking up the fractions, just practice, I should say. You don't want to get caught up trying to solve for the letters. You're going to give yourself a really hard time. But to notice, this is still a proper fraction. Even if this was an x squared or even an x cubed, it's still a proper fraction. This is already factored, but even though it's factored, this is a degree 1 factor, this is a degree 1 factor, this is a degree 1 factor, but it's squared. Combine all of that, and this would have been a degree 4 polynomial in the denominator. So once again, it is proper, so I can go right into the decomposition. And now, this is the more common way we do it. We just kind of go from left to right, and we just keep putting fractions for, again, fractions for every factor in the denominator and for every power of every factor. So I start with an x in the denominator, and that's still a very basic 1x to the first power, so we just get an a on top. Plus, now I get an x minus 4 for my next fraction for the denominator. And that's still a basic factor, so that'll just get a b on it. Plus, now this is where some people get into trouble. And there are some slight variations on what works, but here's the best habit. Again, like I said on the previous page, a fraction for every power of this factor. This is squared, so that means I'm going to need a fraction for x plus 1 to the first power, and I'm going to need a fraction for x plus 1 quantity squared. But the factor itself is still just an x to the first, so both of these, and that's in both cases, even though this is being squared at the end, the factor itself is just to the first power, so they still just get a basic number. A basic, maybe this is a plus 5 over this, maybe this is a minus 2 over that, and that's all we can get. Pause for one moment. Some people might say, well, wait a second. Ultimately, though this would be squared, can't this also have an x on top? That's where, and it would still, you're correct. That would still be a proper fraction. If I had, say, dx plus e, because I don't know if it's just an x, maybe it's a 4x. And then maybe it also has the numerical part as well, just the way this one is. That's proper. Even if it was just over x squared, that would still be a proper fraction. But it's redundant. It's unnecessary. The fact that you have this and this one will take care of those more basics. If you had 2x plus 1 over this, well, that could be broken up into a smaller one and that higher one. So that may sound a little confusing, but hopefully number 3 will clear that up. So number 3, let's look at 4x squared minus x plus 10 all over x minus 2 quantity cubed times x squared plus 1. Once again, it is fully factored. There's nothing more we can do. And don't be fooled here, right? That's not x plus 1 times x plus 1. This and this are completely different situations. If you actually FOIL it out, you get x squared plus 2x plus 1, so don't make that little mistake. So now, this to the third power, well, I've got to get a factor to the first power, that same factor to the second power, that same factor to the third power. That is, again, a fraction for every power of that specific factor. Not just the last power, not just the first and the last, every power all the way up. I mean, even thinking about this with regular fractions and numbers. If I was trying to get a common denominator, and I had one fraction had a denominator of 3, another one had a denominator of 9, another one had a denominator of 27, they're all powers of 3. So again, it's not just they all break down to just 3. You need all the separate powers of 3. 4 over 9, that's 3 squared, does not become something over 3. 2 over 27 cannot be written as something to the 3 squared power and cannot be written as something to the first power. So once again, you need all of those, but just like this piece up here, the factor itself is all degree 1. It's all x to the first. So once again, we just get those plain simple letters, but the last one, that last factor is degree 2. And it's not degree 2 because it was a degree 1 factor raised to a higher power. That is a degree 2 situation. Go back to what we saw right here. That is exactly the same thing. So it's not just an x term, it's not just a number. It might only have one, it might only have the other, but we have to have the possibility for both. So this one is going to need a something times an x possibility plus a number by itself possibility. Okay, one more. Like I said, we're really not going to, for the problems we solve, we're not going to really have to go past C. But just to get this full experience with the decomposition, let's just finish with one more. Oh, and by the way, again, this was proper fraction. I hope you notice, just setting up the decomposition, the numerator is irrelevant. Outside of the numerator, again, having the right degree so that the numerator is a lower degree than the denominator, the numerator is irrelevant for the decomposition part. When we solve for A, B, C, D, etc., that's where the numerator is going to become more important and is going to become very necessary again. But just for this breakdown, just this part of the setup, it's just about the denominator. Just having it fully factored and getting to this part. So number 4, let's look at x cubed plus 5x minus 1. And let's have x cubed times x squared plus 4 to the second power. Remember, when it comes to factoring, your factors, this really goes back to a lot of algebra. All polynomials can be broken down into what we call linear and quadratic factors. So if you have an x cubed plus 1 left, you could still keep factoring. But anything, once you get down to the second degree, some things can still keep going, but others cannot. So again, this one is stuck. So there's nothing more I can do in this denominator. It is already fully factored. And even here, this is a very, very common mistake. People go, oh, the factor is cubed. No, no, no. Just like we saw up here, the factor was x plus 1. The factor is degree 1, and it happens to be squared. That's the same idea here. I mean, we don't write this as x minus 0 cubed, but that's the way we want to think of it, so that I would have an x minus 0, an x minus 0 squared, and an x minus 0 cubed. All powers of the factor itself. So an a over this, a b over this, a c over this, because again, the factor itself was just an x to the first power. Just want to make that note. That was the degree here. We weren't using that as a factor, but here that's just a rewrite to make that same connection. But now here, we're going to need an x squared plus 4 to the first power. We're also going to need an x squared plus 4 quantity squared. So just like we were seeing here, and similar up here as well, every power of the factor is represented. But now just like we did here, that doesn't change the top. It's a degree 2. It can get an x term and a constant term. But then this one is also degree 2. So I'd have an fx plus g. That is the idea of decomposition. So again, I wanted you to have some experience with this, but you'll see the problems that we really solve with this one is a very easy one. Not to, demean it. It's still a very good problem to be able to solve, but we'll see some ones that are a little more complicated than this as well. But when we get to those, again, the decomposition is not that bad. I just want you to have practice, if there ever were tougher cases, that you understand how to set them up. Okay, so now let's actually get into solving, evaluating the integral. And we're still going to start off back with that first one. Minus 7 over x squared minus x minus 12. Overall, just want to point out, in your book, I believe it's examples 2, 3, and 5 are all really good. Again, I don't want to always call them basic. They're at this level or maybe that slightly next level. These are all very good ones to consider. I believe examples 7 and 8 give you more practice with the decomposition. And then that last little idea we talk about, that rationalization idea, that is another good follow-up in your book, is example 9. But again, we are going to do quite a few examples in this video and in part 2 as well. So lots of practice in the videos, good extra practice from the book as well, and plenty of homework to really get good at all these little nuances. So here, and hopefully as we've been going through all this, when do you apply partial fraction decomposition? You know, I started off pointing out there are no set in stone rules. Integrals are still more complicated than derivatives because we just have guidelines. But hopefully as you've been practicing all these sections, you recognize some of the more friendly integration by parts problems. So they may initially look like a mess, but you already have a good sense integration by parts looks like it could work. The trig integrals are just all the trig functions. So those are fairly easy to identify, but you need lots of practice to make sure you know all the manipulations to get something you can solve. The trig substitution starts friendly, one of those radical forms, the radical x squared plus a squared minus x squared minus a squared. Those at least stand out to get us started, but then still a lot of tough stuff that comes after. But I'm trying to point out right here that there are a lot of good indicators that try and put you on the right path. What technique even has a possibility of working? And for all these, again, we're talking about those polynomial over polynomial situations. So that's exactly what we're looking at here. We said that right off the bat on that very first page when we first saw that. That didn't look so terrible, and you might have tried u as the denominator, but it doesn't work. So what I like to do is focus on the partial fraction work off on the side and then come back and solve the integral itself, to almost kind of keep these as two very separate steps. So we've got the minus 7, and we already saw how that factored, x minus 4 times x plus 3. And we already up top here broke that into a over x plus 3 plus b over x minus 4. So we started off with the actual decomposition. But now step 2 is to actually solve for a and b. And the way to do this is to clear the fractions. There's a couple little techniques I'll show you at the end, but for this next step, we're all on the same page. We clear the fractions. So I'm going to multiply everything by that common denominator, x plus 3, x minus 4. Left side of the equation, everything cancels. I'm just left with the minus 7. The right side of the equation, well, right here, the x plus 3's cancel. I get a times the term x minus 4. Plus, reset all of this now times this fraction, and this times the x minus 4's cancel, so I get b times x plus 3. So all of us need to get to here, and now from here, there's two techniques that people can successfully use to finish solving this. Number one, this, for some of you who stay with math, a later follow-up class, it's not directly a follow-up to Calc 2, but many students take linear algebra, and they solve much more complicated equations like this, but that's one way. We'll make this into a system of equations, and I'll show you that in just one moment. And again, basic systems. These can be pretty complicated, but the ones we solve won't be that bad. But the other technique is the clever X technique. You want to find values for A and B separately, one at a time. But right now, this is one equation with three variables, X, A, and B. So the clever X technique is all about picking clever X's. Let X be a value so that you could fill in that value for X, and that eliminates one variable. But you're not just picking any random value for X. You want to pick a value for X that'll make one of the A or the B, one of those terms, go to 0. So for instance, if I let X equal -3, technically I would plug that in both the left and the right. There's no X's over here, so the left side is still just -7. Over here, well, I would plug that in. -3 minus 4 is -7, and that's still times A. But over here, -3 plus 3 is 0, and 0 times B is 0. That's the idea of the clever X. You plugged in a value for X, so that variable is gone. You still have some variable left, but the other variable, or others, plural, go away. So, that's not random, everybody. You know, some people, just a little practice, we realize we're looking at this line. And we're looking, how do I make this 0 to make the whole thing 0? Pick the X that makes this whole thing 0, and then we'll do something similar over here. The order we do this doesn't matter. We just have to get all the answers. So when I pick this X, I knew I was eliminating B, and then I would be able to solve for A, right? Divide both sides by -7. And we get our first answer, A equals 1. And then when I let, now X will be 4. Again, I'm not just recopying the left side. If there were any X's left here, I would plug that X value in there as well. But now when I plug it on this side, now this becomes my 0. And then I get 7B. Finish solving for B, divide by 7. And B is -1. And again, go back. We see that matches. And that finishes this problem. Okay, I'll recopy it here in the notes very quickly. And technically I had 1 over X plus 3 plus a -1 over X minus 4. But that's where I was saying earlier, ending up with a negative value for one of these coefficients, well, that just can be kicked out as a negative sign. And then again, both of these, treat them as two separate. And there is your answer to number 1. Just like all the other ones, everybody, I am focusing on the antiderivative. If this is a definite integral, say it goes from 0 to 1, well, bar, and you still have the 0 and 1, and you still have to plug in. But we're really, again, we're not focusing on that part. We're focusing on the antiderivative component. So that is the clever X technique. Issues, well, you'll see as we go along. There are a lot of problems where the clever X technique is very friendly, but there are a couple little hiccups. So no matter how much you like this technique, you still have to at least be aware of the other technique. The other technique, let me just draw a little line here, still the same problem. We're going to end up with the same solutions for A and B. So therefore, we'll end up with the same breakdown of this original integral and the same answer. But picking up from right here, what we will do is multiply these out. So I'll get AX minus 4A plus BX plus 3B. And what we are going to do, we are going to turn this one equation into a system of equations, and we're going to do it by just looking at common terms, like terms. So how can this right side add up to be this left side? Well, we have to realize here that we don't have any x terms. We have x terms here, but we didn't have any x terms here. Well, I could force that in. I could treat that like a 0x. And then I have constant terms here. Those constant terms are going to have to add to give me the constant term here. Right? That's how algebra works. How can the right side equal the left? The x terms are going to have to combine to give me this x term, and the constant terms combine to give me this constant term. That allows me to make a system of equations from the x's. Because now that we have the like terms, how does this add up to 0x? Well, we just add the coefficients in front. So looking at the x line, 0 has to come from adding a plus b together. Literally 0x equals ax plus bx, but now the x is not necessary. And there's my first equation. Second equation, the constant term. How do we get that? Well, it comes from this constant term plus this constant term. Now, what we were able to do here, we took one equation with 3 variables, cleverly distributed, so now we can group these together. So again, this was the x equation, and this was the constant equation. So this one equation with 3 variables became 2 equations with 2 variables. Now I don't need any powers of x anymore. Now it's all just about the a's and the b's. How can you finish solving this? Again, algebra, systems of equations. There are 3 main techniques people are familiar with. Substitution, solve one equation for one letter, substitute that into the other equation for that letter. So here, like if I subtracted the b, a equals negative b. Well, now this a can be replaced with a negative b. So I'd have minus 7, minus 4 times minus b plus 3b, and you could solve that for b. And then you could back sub and solve for a. That's one way. Some people like substitution. Other people like this idea called elimination. The third technique is graphing. You really don't want to graph. You know, these you'd have to be thinking about, well, what's your y, what's your x? It's really a mess. So it really should just be the 2. Substitution or elimination. Remember the idea of elimination. You're going to multiply one of these equations by something so that you'll have a perfect matching variable with opposite signs. For instance, if I multiply this top equation by 4, that would give me a positive 4a. That would cancel perfectly with this minus 4a. So let me do that. I said all the steps for the substitution, so you should be able to copy that if you prefer. But for the elimination, I multiply everything by 4. The alternative would be eliminate the b's and multiply by negative 3, so that a minus 3b would cancel with a positive 3b. But whichever you do, kind of like what we saw up here, it's not random. Some people with the clever X technique, they realize it's all about just making the factors equal to 0. So they just kind of keep randomly plugging in and just dealing with what's left behind. But with some good practice, we should be able to see it in advance. By using this value for X, we would eliminate B, therefore we could solve for A. By using this value for X, we would eliminate A, therefore we can solve for B. So I hope with your elimination technique, if you're choosing to do that here, again, you've got something similar. It's not just randomly multiplying. You've got more of a plan. And now you're literally adding these equations. So that's just adding all the like terms. 0 plus a negative 7 is negative 7. These cancel as we said. There's 7b. Solve for b. You get negative 1. And then once you have a value for one variable, plug into either the original, solve for the other, and you'll get A as positive 1. Okay, so next part, this is only part 1. There's a lot of information to go through, but now for the next part, we really just want to get more practice setting up the partial fraction decomposition, solving for the letters, and then that last little part, finishing the integral. I gotta say, I don't want to say it's a common mistake, but it's a mistake I hate to see. People do all this good work, get the letters, and then forget to finish the problem. This should be the hard part, everybody. We need some practice to get used to the decomposition. We need some practice solving for these missing variables. But then at the end, if we've been doing well through chapter 6 and chapter 7 up to here, these integrals, I'm not saying they're all easy, but that should be the easier part of the problem. But just make sure we finish that part.